Well, gentlemen, we are to commence. In fact, the session is scheduled between 2 to 3:30, and since we had closed our earlier session a little late by nearly half an hour, we have to allow that allowance. So, in other words, our commencement could be, say, 14:30 hours, and it has to also be concluded, in all fairness, by 16 or 4 p.m. And to gain time, pending arrival of all those who are yet to join us, we have still 5 minutes. If you all agree, we immediately commence the session. So thank you very much. Now this session is focused on risk assessment and emergency preparedness. And we have 5 response papers. 2 are DRIP specific. One is the current practice topic, and another is a research topic. In all, 5 presentations are to be done, and following the earlier norms, 10 to 12 minutes for each presenter would be possible, allowable, without much difficulty. So if you can conclude as per this norm, it would encourage a lot of discussion subsequently, which would give you additional time by way of response. Without loss of time, if the first presentation of degree of risk of dam failure, if our colleague, Chief Engineer from Maharashtra, Mr. Ramesh Nikum, is available, I request him to commence.
Hello, my paper is degree of risk of dam failure. In India, large dams as per ICOL definition are 5,202, and in Maharashtra, as per 2009 census, 1,845, above 35%. As per February 2015, there are 2,132 dams, which is 41%. Reservoirs are formed by dams, while reservoirs are designed and operated to reduce the risk such as water shortage, downstream flooding. They inevitably create a new risk of dam failure. Risk is characteristically of low probability, but can be of high consequence, with the potential for life loss in addition to economic and environmental damage and social disruptions. The distributions of project benefits and dam failure consequences are seldom congruent. This can result in conflict between the beneficiaries of reservoir project and those whose lives and livelihoods are placed at risk. In many cases, downstream development has increased the hazard associated with the dam failure. Today, engineering practice yields more severe safety violation, floods and earthquake than most existing dams were designed. This paper discusses the necessity of introduction of approach for prediction of risk of failure in future with the magnitude of in easiest way, that is degree of risk. One of the new method for calculating degree of risk may help to forecast dam failure consequences for managing prior repairs, maintenance and operation of dam. Degree of risk can be calculated on arithmetic basis by considering numerical value of vulnerability. Numerical value of vulnerability calculated on the basis of physical parameters and variable parameters. Degree of risk calculated on the arithmetic basis by considering numerical value of vulnerability and potential consequence of dam failure. This vulnerability calculated on basis of physical parameters and variable parameters. Physical parameters like dam height, type of dam, impounding capacity of dam, type of foundation. Variable parameters like dam age, spillway waste wear age, seismicity, reliability of discharge faculty, and dam conditions. Dam classification can be classified based on degree of risk. It poses to person and property, says it as P equal to V into C, where P is the degree of risk, V is a numerical value of vulnerability, and C is numerical value of potential consequence of dam failure. According to the dam can be classified into 4 classes A to D. P according to P value ranging more than 120 dam is classified as A, 70 to 120 is B, 25 to 70 is C, and less than 25 is D. Dam vulnerability. The vulnerability of dam is measured by multiplying the arithmetic mean value of constant physical parameters alpha, that is noted as alpha, by arithmetic mean value of variable parameters beta. Dam vulnerability is V equal to alpha dash into beta dash. Alpha dash is average value of constant physical parameters, as we mentioned earlier. Alpha 1, alpha 2, alpha 4, and beta is beta 1 to 5. Constant physical parameters, we have assigned the figures for various dam heights. We have given a point. We have assigned figures as less than 5, 1 point, 10, 2 point, 20, 3.5. This table is tabulated. Points are tabulated here. For intermediate heights, we can interpolate the points. Dam type alpha 2, dam type concrete arch is 1 point, concrete gravity is 2 point, concrete buttress is 3 points, rock fill dam is concrete facing 3 points, upstream earth core, and earthen dam 10 points. Impounding capacity alpha 3 capacity is various capacities. We have given assigned points 1 to 10. Foundation type alpha 4, we have various points, various conditions of foundations. We have given points 1 to 10. Treated basalt rock 1, basalt rock, treated rock other than basalt 3, rock other than basalt 4, treated clay 6, and other 7, treated alluvial deposit 8, alluvial unknown deposit 10. The variable parameter beta to be considered on age of dam, age of spillway, waste wear, seismicity zone, reliability of discharge facilities, and condition of dam. Beta 1, that is concrete dam, age 0 to 50 and above, points are given 1 to 20, and embankment dam 1 to 60 and above, points given 25 to 2. Spillway age, there are points assigned 5 to 10, seismicity points assigned are 1 to 8 for various zones. Beta 4, reliability of discharge, satisfactory discharge 0.1, acceptable 5, unsatisfactory or unknown 10. Dam condition beta 5 condition, very good 1, good 3. These are very good is dam does not show any evidence of any deficiencies. Condition of dam good, the dam shows evidence of dam only minor deficiency. Acceptable, dam shows evidence of deficiency requiring repairs without immediate endangering the dam. And poor or unknown, the dam shows evidence of single or multiple serious deficiencies. Dam failure consequences, numerical value is given. We have classified in categories very low, moderate, high, very high, and severe. Points given, point assigned are 2 to 25. The various categories has dam failure consequences. Very low means uninhabited area, area containing minimum infrastructure, such as second dam in low, very low consequence category, reservoir access road, farmland, occasionally inhabited, low condition, occasionally inhabited, area containing less than 10 cottages or accommodation for less than 25 persons, limited infrastructure. Dam failure moderate, permanent inhabited area containing less than 10 residents or 10 more cottages. Various conditions we have tried to classify and given the numbers so as to arrive the figure of dam failure. This is severe condition, classified permanent inhabited area, population more than 10,000 and substantial infrastructure area containing. This is reference to 19th American Congress. We have tried and we have calculated on this for prioritization. Thank you.
follow the same procedure as we did earlier. Allow all the presentation to be through and then come back to you. But definitely, right now we want interaction. Okay, we allow. Mr. Patak from World Bank, huh?
No.
You don't want?
Okay. Yeah, Ambi Valley. Ambi Valley Dam. It's a private dam, Ambi Valley. We inspect this dam regularly. Ambi Valley. Yeah.
Well, we are going to ask you later, and in the meanwhile, you can get yourself prepared. This you have taken from the US categorization.
Yeah.
You see the dam safety program in the morning also I was trying to indicate when I was mentioning the impending bill, dam safety bill to be enacted in the parliament. It will also be trying to take on board the Indian situation.
Yeah.
How far now the hazard classification that you have tried to project is relevant for a country like ours? Don't immediately answer, think it over.
Okay.
And I incidentally would also ask you whether you had an occasion to go through the guidelines with regard to design of seismic dams, the national guidelines, together with the National Committee on Seismic Design Parameters.
No.
There is a guideline in which risk as well as hazards have been captured.
Yeah.
And there is an ICOL bulletin on this subject, and the INCOL bulletin is also available on this. And the ICOL bulletin has undergone revision only last but 1 year. And unless you are able to see all this through simultaneously, bringing out something would be a little bit debatable. So keep it in view, and I am sure more questions would come. And we thank you for bringing this paper right at the first instance.
Thank you. Thank you.
Thank you. We give a big hand. The next paper of DRIP category is on the Emergency Action Plan, Implementation for DRIP Dams. Antonio Porchedu, you are welcome.
So, good evening, good afternoon actually. Today we are going to speak about the emergency action plan for the dams. An emergency action plan is a formal plan that identifies potential emergency condition at a dam and prescribes the procedure to be followed to minimize loss of life and property damages. So an emergency action plan is a plan that is not intended to be used for normal daily operation or for normal operation of the dam. It's a plan that is intended to be used only in occasion of emergency, a special emergency. An emergency on a dam is defined or can be defined as a condition which develops unexpectedly and endangers the structural integrity of the dam and the safety of life and properties downstream. It is such an event that requires an immediate responsive action. The EAP, the Emergency Action Plan, is that document that has to be used in case of emergency. Emergency is generated either by a dam break or by an important release of water from spillway. In the EAP are identified the roles and responsibility of dam owner and of the authority in charge to manage the emergency and evacuate the people. Furthermore, it categorizes the emergency types and specify the action to be implemented in different types of emergency condition. But why to have an emergency action plan? Emergency action plan is mainly intended to reduce the risk. The risk that is connected essentially and intrinsically with the presence of the dam on the territory. And how to reduce this risk? Usually approach to reduce this risk are with structural measure or with non-structural measure. Structural measures are listed on the slide, And they usually are not so safe because they can create a false sense of security due to their physical presence. And frequently, this kind of measure can lead to an inappropriate use of the areas downstream of the dam. So people can feel safe and they can start to build. They can start to urbanize areas that should not be urbanized. That's the false sense of security that they give. This was a dam where some structural measures were implemented, but nevertheless, the dam was swept off. One dam, and in the second, where important structural measures were implemented on the structure, the spillway was swept away. So, structural measures are important, are essential to be implemented, but we have also to think about non-structural measures. And the emergency action plan is a non-structural measure. The risk is obviously connected to the type of dam, to the location of dam, and as we have found out within our project, also with some particular elements like the spillway inadequacy or problem connected to seepage through the dam, leakage, or inadequacy of mechanical equipment or malfunctioning. So the preparation of emergency action plan is essentially to manage, to be able, in case of emergency, to manage effectively this risk. What is the structure of the emergency action plan, essentially? So, in the emergency action plan, we should identify the dam. We should give some basic information regarding the dam and some important information regarding hydrology and hydraulics. In particular, we have to insert inside the emergency action plan the inundation map, as we know, are the final output of the dam break study and of some flood routing studies. So the dam break is an important element. Dam break study and inundation map is an important element of the EAP. Important and probably essential, because without this information, we are not able to understand what can happen downstream in case of emergency. In addition, the EAP should contain specification regarding roles and responsibilities of the authorities which are involved in the management of the plan. And these authorities are essentially These authorities are essentially the dam owner, who has to take care of all the procedure regarding the dam and in the dam's area, and dam authorities, and public authorities, sorry. Public authorities have to take care of evacuation and to save life. Public authorities are usually collector and civil protection service. So emergency has to be managed upstream by the dam owner and downstream by the collector. So after definition of basic information, after collecting the basic information regarding the dam, after definition and the collection of the basic information regarding the dam, is necessary to go to the definition of role and responsibility, and therefore identify a procedure to implement, to manage in an operational way the emergency. We have selected a particular straightforward procedure articulated in 5 steps to do this. the procedure is articulated in a first step where we detect the emergency, a second steps with level determination. It means we identify the seriousness of the emergency. Then we provide with the notification and communication. And then, in accordance to the emergency level identified, we have some expected action. In this chart is summarized there is an outlook of the five steps procedure. The first step is the event detection. Whoever at the dam site or in the reservoir area can identify an unusual event, can be seepage, can be a settlement of the embankment, can be a problem of a spillway, can be an unusual reading of instrumentation. So whatever event is unusual has to be reported to the dam owner, and the dam owner has to investigate about it and go to step 2, identify the emergency level. So the dam owner with his staff has to assess the situation and identify, understand if the emergency is an emergency level 1, that is in reality classified as a non-emergency incident, but that can slowly develop to a more serious situation. Or we can have an emergency level 2. It means that there is a potential dam failure situation. And the situation is rapidly developing and could develop to the emergency situation 3. That is an urgent situation, a very dangerous situation because the dam failure is imminent or is in progress. Once the emergency level have been identified, we have to proceed with the notification of the emergency to the authorities which are in charge of managing the emergency. And we have to do this in accordance to the role and responsibility that we have already identified in the previous phase. Obviously, depending on the emergency level, there will be different authorities involved. Then, the next steps, probably the most important, but no, I would say all are important. The most important, all are important, yes, is to identify, to understand what we have to do. So the expected action. We have to identify for every emergency level some expected action. It means that, for example, for emergency level 1, that is usually a non-emergency situation, we should increase the inspection at the dam. We should monitor the dam for a potential evolution of the problem. And we should also inspect the reservoir, because, as we know, it's not only the dam that can have problem, the dam itself, the body of the dam and of the spillway, but also the reservoir. In a condition of emergency level 2, we have to save the dam if possible. Save the dam means not to have a flood downstream, so it means implicitly also to save life of people. And also we have to think about evacuation of area downstream. And we should start the first procedure of evacuation. While for emergency level 3, the more critical, we have to proceed immediately with evacuation and with the road closure. The last step is the termination of this procedure. And the termination has to be given by the executive engineer, usually. So, this is the general structure. And to summarize, let's go to the end. What we are doing for the emergency action plan within our program, within our activity. We are working both on capacity building and on institutional strengthening. We are in capacity building, we are updating and producing new guidelines, both on EAP preparation and on the break analysis. On the institutional training, we are giving training to states in order to give them the tools, all the necessary tools to prepare the emergency action plan and or outsource it, but when they outsource, they know what they have to check and how they have to manage the outsourcing procedure. So the expected results is that within the end of our project, we'll be able, through the SPMUs, obviously, through the state, to complete and to prepare the emergency action plan for all the states. I think my time is over. Thank you. Thank you.
I now invite Dr. Somendra Puri to present the paper on the two-dimensional dynamic force simulation model for preparing EAP.
Should I start? Good afternoon. The topic is a two-dimensional dam break flow simulation model for preparing emergency action plans. The outline of the presentation is dams in India, dam break modeling, model verification and validation, and then EAP for dam break failures and conclusions. So, in India, there are approximately 5,100 large dams, and some of them are under construction, I think. And these dams, they play important roles in providing socio-economic and environmental resources. But due to insufficient funds, it has become very difficult to maintain these dams. So there is a risk to dam failure, and once a dam fails, that means the downstream side will be inundated, and not only that, there will be cascading failures. If a dam fails, then because of that, there other critical infrastructures in the downstream side may also fail. So maybe for that we need EAP, Emergency Action Plan for Dam Break Floods. So as per the CWC 2006 report, the elements of Emergency Action Plan are notification of flowcharts, responsibilities, emergency identification, notification procedure, preventive action, inundation map, and the appendices. Now, the model, especially flow model, two-dimensional model, that can help us generate inundation map. So I will highlight my presentation. I'll limit my presentation on how to prepare inundation map. So let's say if we simulate any dam site, then we can prepare inundation maps like this. These lines are wave fronts at different times. But we can represent another thing, like let's say in the downstream side, if there are critical infrastructures like transformer, hospital, all these things, then we can plot another thing that is called failure front. Means at what time this critical infrastructure will fail. So like that we can prepare another kind of map on top of this. So available dam break flow models, there are plenty of models in the market, and freely softwares are also available. So 1D popular model is Mike 11. This is commercial, and this is a free one, HECRAS. And in 2D, Mike 21, this is commercial one. Two flow Clopex, they are freely available. But there are limitations of these available models, like Mike 11, Mike 21, we cannot modify or we cannot adjust as per our requirements. And these, like two flow Clopex, they don't have, I think, a proper interface also. So not only that, this dam break model, we can use it for preparing EAP. Not only that, we can use it, let's say a dam is likely to failure just in a 1 hour or 2 hours. Then what will be the likely inundation map? In that case, we need very high speed computation. So those things are not there in Mike 11, Mike 21. So in that case, now recent trend is GPU computation, graphics processing unit computation. So that type of thing we can implement in our model. And then we can integrate it with the GIS software, because GIS is very good for pre-processing and post-processing the data. So the data means flow throughout the system will be very smooth. So here I have developed one 2D model based on unstructured quadrilateral grid. So we are using mainly 2D shallow water equation, and I'm solving it with the help of explicit forward Euler scheme and finite volume method. And this is second order accurate, and the grid is unstructured quadrilateral, means we can define any kind of geometry, irregular geometry. So first of all, I will present some simple cases, laboratory test cases. These are used to check the accuracy of a model. So this is from the experiment conducted by Fraccarello and Toro. This is like a floodplain in this side, and in this side this is a dam, and there is a small dam here. This is the reservoir side, and here I have used unstructured grid, and different stations are there. Now, if the dam fails here from this length to this length, then we can compare our results with the observed data. So we have compared the data results at different stations. And next, this is another experimental case by Belos. So this is the dam is like the boundary is irregular. So there are 3 stations, one here, and here, and we have compared the results. So this is the grid, and this is the comparison. And this is another case. These test cases are very common for dam break model verification. So this is a dam kind of thing, and in this side there is a wall. So if this dam fails, then what will happen? This water will move to this side, part of the wave will come back, it will hit the wall, again it will go. So it is like a wave propagation in the front and back. So this is the comparison at different stations. Now this is one hypothetical dam break scenario. This I have done for Sardis Lake in Mississippi State in USA. So this is the dam site, and in this side there is a lake. Now what will happen if there is a partial bridge? This I have done for 5-meter bridge. Can you please click on the image? So this is the inundation I have plotted dynamically. Now, for preparation of EAP for dam break flood, this flood can take place for sudden uncontrolled release, then excessive controlled release, or release caused by damage to or failure of the dam. So imagine in India there are 5,000 dams, large dams, and there are few thousand small dams. So we cannot prepare EAP for everything. It's a tremendous job, expensive job. So we can classify the dams, low hazard dams, significant hazard dams, and high hazard dams. Generally, for low hazard dams, we don't need EAP. And for some of the significant hazard dams, maybe we need EAP. But for high hazard dams, we definitely need EAP. So this type of model, like a dam break model, they can give information, the extent of the flooded area, spatial distribution of flood depth at various times, then spatial distribution of flood velocities in two directions, and then flood arrival time at each point, and then duration of the flood at each point of the computational domain. Now, this is one model what I have prepared already, but what can be the right model for EAP? Because sometimes we may not invest too much money just to prepare EAP for so many dams. So how can we reduce that kind of thing? So maybe we can go for the web-based remote computation. Like at the user end, there will be ordinary desktop or laptop. From there, the user will give minimum data. Then through web, it will come to the remote server, and we can do the computation. And then the maps will be transferred to the user end. So minimal user input means we can give dam location and height, then reservoir maximum volume. Then we have to identify the bridge locations on the map. Reservoir bathymetry may not record because you can calculate also based on the volume. And then at the user end, we don't need expensive workstation or GIS software and all these things. Then we can go for the simulation in the remote server and transfer of selective maps to the user for EAP preparation. I think I have one more slide. Thank you. Yeah. So these are the conclusions. Thank you.
Can I have? A very good afternoon to all of you. This paper, as it reads, Integrated Geophysical Approach for Dam Health Checks. Ideally, it falls in the category of health monitoring of dams. But since we are talking of risk assessment, we can present it in this session as well, where it has been put. So I'll try to quickly go to the subject here. I'll skip certain slides for the time limitation. I happen to be from University of Roorkee, from IIT Roorkee, where I think Mr. Chairman is from, so I have privileged to be standing here and presenting this paper as he chairs this session. And now once we talk about geophysical investigations, many of you might have seen these pictures, which are very easily understood. These are all medical images, as we see. You have ultrasound, MRI, CT scan, X-ray, etc. Now in geophysical investigation, we are trying to create the same kind of images for the subsurface. So geophysics is not limited to dam investigation. It is being used in various applications, including oil and gas investigation, mining, etc., etc. Here we are obviously going to limit ourselves to dam investigations. So idea is to put effort and create images to understand what is the internal structure of the dam. What are the anomalous zones inside the dam? What is the internal condition of the dam? As we have seen in all the three papers which are presented before that, we are talking of the condition of the dam. At present, most of the condition assessment is based on physical inspections. This is geophysics is a tool which is providing us means to find out the physical properties of the dam structure, dam internal structure, without any drilling, and that's how it aids a lot in the understanding of the dam condition. So this just compare the pictures which you saw earlier with medical imaging to geophysical imaging. Like shear zone, a cavity, this is a concrete dam showing the anomalous zone, the fracture zones in the concrete dam which was done between downstream and upstream wall, concrete rebars in the concrete, buried utilities or pipes and things like this. So of course, as we look at this comparison, it becomes very clear that why it's so important to use these methods and why more and more application is required for most of the dams now, because it gives you a detailed investigation of site, which saves huge cost towards change plans, project delays when surprises crop up. Rapid coverage, you don't have to do any drilling, no digging, vast information is obtained at a fraction of time and cost. In fact, a dam can be investigated anything between 3 to 7 days of time. So even if you have very quick information need on a particular dam, in case of even initial stages of distress, this can be used. It's totally non-destructive, of course, and it's good for early stage application for better planning and smooth execution. Now in dam investigation, we have various methods which are listed here. There are various issues and concerns of concrete dam like cracks and degradation, earth embankment dams like water leaks, landslides, sinkholes, masonry dams like water leaks, strength concerns. There are various methods available for that. I'm not going to read through it. In fact, you have a paper on this already in the kit with you. So I'm not going, I'll just show you certain examples of how it looks like. Now this is the first method, very, very important, what we call electrical resistivity imaging, which gives you a vertical section of electrical properties. So this is a very strong method to understand where in the dam saturated zones have developed. Of course, dam failure is not something which happens suddenly. There are anomalous zones which develop over a period of time, the water saturation increases, and then it leads to failure or problems in the dam. Most of the time, we are only looking when the manifestation of the problem is physical. We are able to see it visually. Here, we are able to see the saturated zones even at the early stage. So this is the way it is done on the, for example, dam top, the crest of the dam. And that's how the results look like. Whatever is the height of the dam, you can plan your survey accordingly and look at the saturated zone or anomalous zone in the dam body. These are examples which have been done from the crest of the dam, and in the dam body, the saturated zones have been picked up using this method. This is an example of cavity. So basically here we are looking at the electrical property, the resistivity, or the converse of resistivity, that's conductivity, and which is directly dependent on water entry in the dam body. So this is a very, very strong method which can be used in earthen dam or masonry dams, very equally here. This is another example where this is a zone. Again here, 80 meters to 50 meters, 30 meters is the investigation, and this is the anomaly which was detected. Under the, this is the bedrock surface. So it was the anomaly under the bedrock. So this kind of anomalies can be detected very effectively using this. And you do number of lines, and by correlating various lines, they can be done, let's say, downstream on the dam crest, and then ultimately you can correlate them and find out the complete zone of anomaly as it is going in the spatial manner. Second strong method which is used is streaming potential. There are certain zones which are anomalous where water accumulation has taken place, but there might not be an active seepage taking place through these zones as of now. Ultimately, if left unattended, tomorrow they might lead to seepage and they can become the seepage paths. Now, streaming potential differentiates between the zone which are only saturated at this time or anomalous at this time, but whether they are contributing to active seepage, which is, let's say, being observed in the downstream, or they are not contributing as of now to the active seepage. So this is the method which works on the potential due to flow. It's a natural potential. So it's like this: when through a porous media, the water is flowing, the positive ions are being displaced, and the current is flowing. And this is the basic fundamental based on which this method is working, is streaming potential. It's like this: is the reservoir, this is the downstream side, and let's say the water is going through this path. So you have the potential, if you do various lines of streaming potential, you see negative potential when the water entry point, positive at the water exit point. Now the strength of this method is that by using this, you can actually plot your complete seepage path, right from upstream to downstream. Because sometimes you can have the seepage coming out from here, but you do not really know what is the origin point of this seepage, which is very important to understand before you start the rehabilitation or the treatment of the dam. So that's the strength of this method. These are a few practical examples from SP. This is, initially we started in '98 using these methods for various dams. This is a very interesting example where you see this, this is a dam in which this was a clear zone of anomaly through which the seepage is taking place, and corresponding SP shows a high negative across this zone. So this becomes clear that the most of the seepage is coming from this zone,
At the same time, there are certain other anomalous zones in the dam also, here, here, and here, which in future might lead to seepage. But at present, there is no seepage coming out from there. It is not being observed in the downstream. No one can suspect that there can be some problem in this zone. So just by visual inspection, if you start the treatment, you will treat this zone and you leave this, and after 5 years, again, you will have active problem through these zones. So this is how you are able to see the anomalies and also which anomalies are contributing actively to seepage. There are various other methods like GPR, which can be used for things like cavity detection or shallow anomalies. It is used for dam inspection to see various interfaces in a dam body. Seismic tomography is again a very, very strong method in which you are able to find the unit properties of the earth material. So it is done by, it can be done across the faces of the dam, downstream face and upstream face. It can be done between the boreholes. So this is the example when sources and receivers are in the boreholes and the surface. It is based on crisscrossing of these rays, and ultimately these rays are being used for a tomography to create. This is the kind of receiver and source arrangement. So this is a dam, and ultimately you are covering the entire dam body by crisscrossing of these rays. This is how it looks like in photograph, the lines, and this is the result. Now you see, here you see P wave velocities. Now this is a concrete dam. Now P wave velocities are dependent on the quality of the concrete. If the concrete is healthy, they will fall somewhere in the red and the yellow zone. But as the concrete is degraded or anomalous zones have developed, you see these are the zones which are having problem. So these are the fracture zones. Now this kind of detailed information is possible when you do tomography across downstream and upstream phases. This also has been done in India, and we happen to be working with the company Solgeo from Italy, which has completed 2 projects of tomography, one in Tungabhadra and second in Chimone in Kerala. So this tomography also has been applied in India, and it has given very detailed information of the internal condition of the dam in both the cases. Then we have seismic refraction, which can be used to find out the depth to the bedrock, and also if there is any problem in the zone just below the bedrock. And that also might be contributing to the seepage or the problem in the dam body. So this is one example in which seismic refraction has been done. This was the bedrock surface, and this was a zone where there was a problem. Now they can be like fracture zones within the bedrock or shear zones within the bedrock, which might not have come in the light at the time of construction, but later they might attribute to the problems with the dam. This is another example of seismic refraction, which also can be used to see the phreatic surface, saturated zone, and unsaturated zone based on P wave velocities. Refraction microtremor is a method which gives you shear wave properties. So it gives you the shear strength of the material, which again becomes very, very important when we are evaluating a masonry structure or a concrete structure. We have also used this method in one of the dam in MP to see the permeability values on the narrow hillside. It was Manikhera Dam, where some weakness was expected. See, this is a dam, this is a bedrock. As you see, this is recent work we have done. This is bedrock. And these are the zones where low velocities, low shear wave velocities have been observed, which are very distinct from the surroundings. It is supposed to be the same quality, but this is different. So this is how you get the shear wave velocities. Shear wave velocities and P wave velocities put together give you all the dynamic modeling: Poisson's ratio, bulk modulus, shear modulus, etc. So ultimately, to conclude, we do the data integration, resistivity image for depth and saturation, SP for flow, GPR for voids, cavities, and interfaces, seismic refraction for P wave velocities, which gives strength, REMI for S wave velocities, shear strength, and tomography for material properties. To conclude, it's a quick assessment of subsurface conditions in non-destructive manner, detailed and continuous information as against drilling, and it's an important tool for health check of dams, regular monitoring, and pre and post rehabilitation inspection. This is one of the most important thing, I think. The health check of dam at the regular interval is something which is very, very important before the problem becomes too critical and we are able to see physical manifestation of the problem. If we are able to do the health check every 5 years or even 10 years of the dams, especially of the dams which are already getting very old, that's one. And second is, when we start the rehabilitation measure, as of now, we generally plan it based on our assessment of where the problem is, based on the physical manifestation of the problem which we see in the dam. The idea is if we do this investigation, we can find out exactly where the problem is, what is the extent of the problem, and then plan rehabilitation measure accordingly. And having done the rehabilitation, we again need to do this to find out what has been the efficacy of rehabilitation. Because just doing a grouting in a dam doesn't really ensure that the dam has been really rehabilitated. That's my conclusion. Thank you very much for your time.
Thank you, sir. Good afternoon. On behalf of DVC, I first feel to acknowledge the organizers of this conference that they have given us a chance to share our experiences in this conference in front of the so high-level dignitaries. Our paper is on overview of Konard Dam on need of rehabilitation, basically why the rehabilitation is required in our dam and what is the potential of this dam that has been described in this presentation. First, I would like to state a few points on the basic problems of these dams and the major problems of the cracks development. And the potential of that includes the water availability studies as well as reservoir sedimentations, present storage capacity, and PMF, how the altered PMF will be accommodated in this reservoir. And at last, I'll conclude over this. This is a pictorial views of our dam. This is the upstream, then the downstream and the top of the Konard Dam. And this is a schematic diagram of our sectional views. The special feature of this dam is just these portions of the hollow spaces that has been built inside the piers between the junctions of the two piers in abutment portions and in underslice portions, as well as it has the three galleries. One is the inspection galleries, then is the access and operating gallery, and then is the drainage gallery. More vulnerable point is that this hollow space saved about 6% of concreting, and moreover, during construction phase, water was put in this hollow space and were used for the concreting purposes. This is a sectional view of this. Here also hollow space is described here also. This is the hollow space. Anyway, the major problem is the partial functioning of the existing hydromechanical equipments, and the cracks in the dam bodies, especially the cracks have been observed at the top level inspection galleries, and more profound cracks were observed at the middle portion of the spillways, and where the depth of the cracks varies from about 0.9 meter to 3.8 meter. And leakage through penstock has been observed, though this leakage has been observed recently, not a very old problem, at the side by side as well as in many places rip-wrap dislocations have also been observed. Now I am showing a few slides of the outer dam of the cracks are shown in the outer dam body and the downstream face of the inspection gallery. We are monitoring through dial gauges. Then downstream face of the inspection gallery. And yes, our DSRP team in 2003, they are visiting in inspection gallery. Many of the experts are also sitting here. This is the operating gallery. Then the special features of this dam is that there is a vertical duct is there. This is the connecting between the different galleries. Then the plumb bob, unfortunately, this power plumb bob is not functioning, and the drainage hole is there. And this is the special features. What I have told that this is the wide space that was created between the junction of the piers and the drainage gallery. Now a few study was carried out on the cracks development. It is observed that at the top there is a plotting of the reservoir level. At the down, the crack width, how it is increasing with respect to time is shown here. And it is observed that the cracks are definitely it is increasing with time, but every year there is a cyclicity, seasonal variation is there. And also it is observed that the crack width expansions are not related or correlated with the reservoir level. But peculiar experience is observed in another point. Here it is observed that the this is the peak width of the crack, which is observed after reaching the reservoir maximum reservoir level throughout the season. So very peculiar behavior has been observed in the crack studies. Again, it is here in different times from 76, the different experts they have visited almost. I think that the most of the factors which may be the probable cause have been described by the different experts time to time, like the variation of the water load, temperature shrinkage, then the arch action, then the tensile stresses, and again expanding action, even structural problems, and WRDTC they have described that the higher tensile stresses that developed between the upstream phases and downstream phases of the gallery. And we think that actually basically no single cause is the main reason for this sort of cracks, the combination of the different cracks, that is the temperature differential. Alkali aggregate reaction in concrete, I think chance is very less, because just now this work has been awarded to the CSMRS for providing to take up these tests, and excessive uplift pressure, then settlement, construction fault, structural problems. And major recommendations were also made time to time. Most of the recommendations covered the regular monitoring of the cracks, then the deformation of the dam body, then to carry out the discharges at the different points, and the measuring of the temperatures, as well as some tests was also described by them experts: sonic experiment, photoelastic, geophysical inspection, stability analysis, underwater examination. And DVC has taken most of the tests carried out very sincerely from its very beginning. Even now, after getting the recommendation of the DSRP members, we have taken up these works. We have given the consultant CSMRS for investigation of and as well as we have been able to include the Konard Dam in the World Bank funding projects. And we hope that we'll get the result of the geophysical investigation by this year. Anyway, now I am coming to the potential of this reservoir. If we find that though catchment area is very small, about 1,000 square kilometer, but 90% dependable flow is 265 MCM, where 175 MCM is present active storage of this reservoir. And this study has been carried out for different seasonal flows, water year, monsoon, as well as dry period. And again, I am coming to another duration. Basically, this water ability study was carried out for different durations, months, even 10 daily durations. But it is a peculiar observation that the mean values of the flow are always, in all the cases, even in the 10 daily flows, we will get that higher than the median flows. So it is a great issue that what will be the central tendency of the flows or discharges, whether we should accept the median values or we should accept the mean values. This is the 10 daily, same views is there. But in this case, we find that in case of the 90% dependable flows, even in the dry period, we are getting a little bit flows, about 2 hectometer, 3 meter. Only one occasion it given as a zero flow. Moreover, because in morning session, a lot of discussion was held on the climate changes, and I was surprised to see that I carried out the changes studies, taking the 54 years data, taking up the 14 methods, parametrical, non-parametric, non-parametric, and short-term dependence, long-term dependence, as well as stationary, non-stationary analysis. And I found that is some changes are there at the 95% confidence level. Out of 13 or 14 figures, in many cases, 6 tests are passing. Anyway, this is the storage status. Already I have described it. The sufficient storages are available. This is the flood releases. Then the probable maximum flood we have calculated on the basis of our hydrometeorological approach. That has also been described in the morning, and so developing the synthetic unit hydrograph. And this is our flood routing studies, and we found that this reservoir will safely carry the PMF. However, it may be, must say that during construction phase or during original design stage, the freeboard was kept much higher than the required design discharge. Maybe that is mentioned there in that, maybe that for the little bit safety purpose of the earthen dam. Anyway, so I want to conclude at the end of my presentation that this reservoir has a high potential. Even the water availability is storage ratio of this reservoir very high, about 0.39. That is the ratio of the active storage and the long-term inflow. And moreover, PAP will be absorbed safely. So some problems are definitely there. If we can rectify through the drip, I believe that our remaining project less like the hydroelectricity, and definitely dam will get the prolonged life. So we'll be able to implement all these things for this dam DVC. Thank you, sir.
Comprehensive presentation. Thank you. We would now, we have also a sponsor's presentation. How would you like it to be? After this presentation, discussion, or before you forget, questions on the speakers or observations on the speaker, and then we take up the sponsor's presentation. Well then, you are invited, Mr. Subramaniam, on Corpy's products and services. But be quick, I really want to float the discussions on your product.
Good afternoon, everybody. I am Subramaniam from Corpitech. It's a presentation on our PVC geomembrane system. Corpy was established in the year 1963, and we are involved in design, supply and installation of waterproofing geomembranes, geocomposites for dams, canals, hydrotunnels, reservoirs and hydraulic structure in general. Geomembranes are thin flexible material with very low permeability. It all manufactured in a factory. They have been used in dams in 1959. Now it is more than 56 years. Geomembrane coupled with geotextile is known as geocomposite, and geomembranes have a constant controlled quality. Dams are, now we apply this geomembrane for leakage problems in the dams. Dams are subject to leakage. There are various reasons for the leakage: distributed seepage, concentrated seepage, foundation seepage, abutment seepage, embankment seepage. And some of the pictures here shown are the status of the leakages in some of the dams in the world. This is causing concern to the owner. This is one of the inspection gallery in Greece, and this inspection gallery in Kadambara Dam in the year 2004. This is when we visited the dam. Conventional methods to repair the leakage have failed. Some of the repair works carried elsewhere. This is a concrete layer, concrete face heavily deteriorated. The work took attend to it with the shotcreting. This is a failure of shotcrete and resin coating. And now, why do we use geomembrane geocomposites? Infiltration in embankments and in hydraulic structure in general, including concrete and RCC, is quite dangerous. Uncontrolled collection and discharge of infiltrating water may lead to collapse of the structure. You can see one of the failure of the dam. A geomembrane would have avoided this accident. This has failed in 2002 in Brazil. A geomembrane would have avoided this accident also. Geomembranes allow construction of dams even with material of limited properties. Uncertainty, unpredicted differential movements. Geomembranes can resist large differential movements because they have high elongation at break. This can also resist large differential movements in fill dams. In RCC dams, concrete shall provide only stability while geomembranes provide efficient water tightness. This is a Mayel Dam in Colombia, 188 meter long height. This is exposed geomembrane in Honduras, 70 meter height. The leakage rate through upstream phase is less than 1 liter per second. There is no repair of the unseen crack was required at the geomembrane once it is covered. Geomembranes can resist large differential movements and rotations between monolith blocks in RCC dams. Geomembranes can be installed in underwater also. This last Creek Dam in 1997, this was done underwater. And this is the right one is before repair, the left one is after repair. And geomembranes, geocomposites have been used for rehabilitation of stone masonry dams. This is exposed PVC geomembrane, surface on which PVC geomembrane has been installed. This stone masonry. For all the presented projects, Corpi provided method statement of the waterproofing system, material, technicians and labor, quality control, management, and one warranty. India has witnessed 2 outstanding applications of waterproofing geomembrane system, one large dam in Tamil Nadu, that is Kadambare, and an hydropower canal in Uttarakhand, that is for NHPC. In both applications, new waterproofing liner is a geocomposite formulated for the site, environmental condition and loads. This is a Kadambare Dam project once it was completed. When we had taken up the job, this was the leakage. And before leakage, the leakage was at a rate of 38,000 liters per minute. After repair, it was 80 liters per minute, for which India Power Awards for that year was awarded to Corpitech. And in case of canal, this is the canal we did in Tanakpur for NHPC. These are all some of the canals we did with the geomembrane. And Tanakpur canal, we did it in 2008. And on completion, when the water was allowed to flow, this is the picture taken. And for that also, Corpi has been awarded with India Power Awards. Now, we are also doing with geocomposite, the hydraulic tunnels. So, I think I covered. Thank you very much. Thank you.
Now the floor is open. You can put your observations, questions, or any other clarifications needed from a particular speaker. I start with the number 1 presentation, degree of risk of dam failure, the Maharashtra presentation. Can you come? Yes. Yeah, please. Any questions to the first speaker of the session? Okay, what is the effort that you have in Maharashtra?
Yeah.
You have now tried to present the scenario that you could obtain from US. Are you working on any particular guidelines, bringing out a sort of a hazard matrix
No, 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 sir.
You don't. You just try to bring the
Yes,
presentation
yes,
from
yes.
outside.
Yes, yes.
And you are completely aware of the existing guidelines with regard to, say, some issues like the determination of seismic design parameters, how to go about?
Not considered here, no.
Okay. No, we do have all these things, how
Yeah.
to classify the risk and how to
Okay.
classify the hazard and how to integrate these two, and
Yeah.
what is the levels that should be kept in view for different types of dam, given their importance, and probably that should be brought into the dam safety things. Since you have already devoted some time and brought this paper, I think you try to work further on that.
Yeah.
For
okay.
instance, you talk about 1,000 or 10,000 or 10 families. We have tried to put in that hazard category
Yeah.
100,000 and above. So now that is debate. That was an initial guideline that
Yeah.
was floated by us in CWC, right, in 93.
Okay.
And INCOLD has also brought out a particular book. CWC has earlier brought out a publication in 96, 97. So you can work further upon them.
Yeah, yeah.
I don't say that it's all inclusive.
Yeah,
Things are continually changing, but look at it critically and come up with the suggestions.
Yeah. Okay, thank you.
Thank you very
Thank
much.
you, thank you.
Number 2
I have a
presentation.
question, sir. So Maharashtra has 35% of dams of India. So they are also pioneer in dam safety, I think. They have taken many advanced topics
Yeah.
of dam safety. That's risk assessment is also a advanced topic they have taken up.
Yeah.
Regarding this design flood estimation, in your case, what has happened? Whether that has increased much? If it has increased much, what is the risk if you are not providing additional spillway to cater the revised design flood? Then what is the risk? Have you calculated that one?
No, 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 no.
It is something
Yeah.
very similar to the
Yeah.
observation at the end of the session by Mr. Jayasinghe.
Yeah.
Your point is, in case we are unable to augment the evacuation capacity by provision of auxiliary spillway, how to deal with that? I think there are two options only, unless somebody else wants to. One is you have to review your life story, rather you enhance the flood cushion, which means you have to revisit the life storage, refix the levels so that you can enhance the flood cushion given the postulated flood levels and that volume that should be absorbed. The other thing is, in case of a smaller one with a lesser hazard downstream, the owner has to take a risk in operating the project, which in our country would not be acceptable. So there are two ways of trying to take on that risk, but whether one likes it or not, that is the flood that, as per the present day science and technology tools, we should carry. We can't negotiate. It is not a bang and key price or trade-off on the prices. This is what it is. Now that also brings, incidentally, I am reminded of the question posed by Mr. Jayasilan in the morning. What happens in the same river basin? You obtain a situation where an upper reservoir is asked to cater to a very high PMF, whereas downstream there is another project which has been designed only for a lesser level. Now this question can be then further extended where you have large number of dams and all. Now the only thing is all those things may have to be revised, but not at one go. Sequentially you have to calculate the hazards associated with each one of the scheme and then try to find the funding and rework, and in as far as possible, if there is a way, divert that excess thing to adjoining floodplains, and we have to see individually case-wise. But this came up in 1984 dam safety conference, something very similar. done by CWC in Nagpur, and there were 3 key papers. One on how to address the structural design for different levels of flood, and the other is on the appropriateness of this PMF, SPF, and also frequency analysis for the determination. I think this should be available in CWC library, and it is worth reproducing this and relooking at it. Many of the IS guidelines, including guidelines for the spillway design, are based on some of the outputs from that conference, in which there was a rich participation by Mr. Hassan, Mr. Mohile, I also, and Mr. Kole was there.
My question is, hello?
Around, that was our first attempt to take this very issue of different projects in a basin, upstream, downstream, catering to different levels of floods as per the revised hydrology. Yes, sir.
Sir, I have a question. Sir, you have arrived some figures by this method, this analysis of risk. You are arriving a figure for any dam. Am I right? By this method.
Yeah.
So, is it endorsed by CWC? Is there any endorsement or any?
No.
No, no, no.
No, it is.
No,
Then
no,
what
it
is
is
the-
not. No.
Then what is the purpose
In
of
conditions,
Yeah.
so it is not endorsed.
No.
And it cannot be a arithmetic calculation. These methods, earthen dam is weaker than a.
So, if
concrete
it is
dam,
there, it is
cannot be
very
said
easy to find out the risk analysis of any dam.
No, it is
Very
not
simple.
that simple. And
Very simple.
No, it is not like that. A designer, whenever he designs any structure, he takes into
No,
account
what I am
all
asking
conditions.
What am I asking is, then what is the theory behind this analysis? If it is not,
We don't know.
if it is not possible.
No, it is not a done under Indian condition. It is, I think, from some paper in from
Yeah,
American
yeah.
journal or
Yes,
some
yes.
they has taken. So please.
Okay, thank you. Thank you.
Excuse me, sir, one question.
Yeah, please.
Sir, my name is Samir Anpinwar. I am JRF at Department of Hydrology, IIT Roorkee. I have
Speak
observed
to
your
the mic and speak louder.
Yeah, sorry. I have observed your slide. One slide was, there was mentioned dam height, and regarding that you have assigned some points, right? So what was the basis behind assigning some points? Rather, you have selected some height, you have assigned 2.5 as a point. So why didn't you choose 2 or 3, or is there any idea or basis on selection?
I think your question was not clear. Best left during tea time discussions mutually.
Okay, fine, sir.
Mr. Jaisira.
See, there are quite a few issues coming out of this. You see, we are talking about risk. There are dams designed for flood absorption. They never follow the rule curves. Because I have made a study of one particular dam which was designed as a flood absorption dam, but it was filled ahead of time when the flood really came. No, there was so much of a criticism that so much release is there. Absorption was lost. Number 2 is inflow forecast we suggest for several large dams, but it is not being considered or implemented. So operation discipline has to be maintained. One more problem, maintenance of gates. It's quite a bit lacking. In some of the major dams, some gates are not operative, but for years together it continues like that. And somehow in some of the projects what I have found is the contract or award system itself is a curse in this issue. Even procurement of a drainage pump purchase has taken 1.5 years for drainage in a gallery. So we cannot take this excuse if there is any calamity. And these are some of the inherent system deficiencies which we have to look into and keep our dams, when we talk about dam safety, these are all very important. Even in a major dam, out of 12 gates, 1 gate cannot operate beyond a half. And if they operate, they are worried about the road that is going to be eroded by the side and they never operate. It so happened in one of the floods, hardly 1 foot of freeboard was left. It exceeded even the MWL. So in such cases, I think we have to take extra measures to protect. Thank you.
No, the point is well taken. You could just capture the anxiety that that was getting revealed from a person like Mr. Jayasilan, who had seen a numerous number of projects. It is of course the same type of reflection by any others, like including me. If you see quite a few projects, you build and then forget about it, never bother to maintain, and when the real flood comes, we get into a sort of difficult situation. We have other system intricacies regarding the award of tender, delivery and all. I think we have to live with that, but then dam safety being an issue which is of concern beyond that of engineers. Probably this can make them work in a little bit differently. The procedures could be different. Like most of the products that are being discussed, the products which we call it the new materials and technology that can assist us to counter the problems, sometimes it is not going to be that easier to opt for that straight away by any dam owner unless they have the backing of those who are governing the entire setup. So even for that sake, the funding agencies insist on proper tendering procedures and all. So to opt for a product which is patented and the cost of which can be questioned, these are all issues that remain before us. But nevertheless, the new technologies give some new tools, new solutions, and if there is a way how to go about it, how to make system changes, we can deal it separately. Maybe a separate session. Pillai should keep it in view. Just like our colleagues in the space research, how they are able to keep to the target. It is the only engineering professional group which is able to project their heads proudly for keeping to targets and really showing that we can do it and we can achieve it. That make in India. We have several made in India. And why these problems? I think it was asked by the chairman of our Andhra Pradesh, generation company, why the structures before 47 and after 47, can we lump it and give them different ranking? So something points to ponder. I have no quick answers for that. But this is an issue. Dam safety asks for rapid decision making. So immediately after one is able to assess the health and then bring out a solution that can yield successful results, how to go about it fast is another dimension that would come up in days to come. But some of the things which you said, maybe the hydromechanical aspects can attract one unique sessions, especially gates and hoists and associated things. Like that Konar Dam presentation, almost that is the case in most of the cases. Tenugat is never operated, lot of, so almost DVC dams have got this type of problems. And the listing starts from 1977 and we are in 2030. 41 years we have been identifying, checking the health. So this is another point to ponder, not in this session. We see, it is you and me who count, how to overcome all the drawbacks that we find in the system. And whosoever has the courage, those who are emerging chairmen of the Central Water Commission, please, we haven't done all that is required. Apologies. You have a lot to do to deal with bureaucracy and the system to come over this. So with that, we proceed further. Our friend is waiting for questions. Yes, Dr. Malhotra.
I fully agree with his observation. The example is DVC. I was going through the project screening templates of DVC. There the hydromechanical equipment has virtually collapsed. There are large number of gates. Out of 12, even 6 are not working. Entire gantry crane is not working. All switch yard panels, etc., non-functional. So it is most important that to keep the hydromechanical equipment in perfect state of health in order to ensure dam safety.
Thank you very much. That only reinforces the argument that I was trying to make. We have Antonio.
Yeah.
And you made a presentation on the approach that you are having. You made, I think most of the presentation that you gave, our people know it. You must have gone through our guidelines, emergency action plan. See what is missing there and try to build upon.
No, I've gone through your guidelines and I review your guidelines, and this is the new approach that we are trying to propose. It's a little bit simplified, because the guidelines, existing guidelines are very complex. So we are trying to use the approach in the existing guideline, but to simplify it in order to be able to prepare a simple emergency action plan.
Thank you very much.
Simple means that it can be easily used by people on the field. So it's not a huge volume of information that sometimes are not practical.
Well, that's very good. Only keep the aspect of how to go about the capacity building. One is, we have lots of documents right from 83, and how to really make it implementable. What way we can strengthen the capacity through academic institutions and research groups, plus those who are managing. And also, I am sure you would touch upon the institutional aspects, which we are having a separate session. Thank you.
Thank you very much.
Dr. Sanjay Rana presented on, Saumendranath Puri. Yeah. Any questions for the 2D dam break flow simulation model preparing EAP? The IIT.
Hello.
Speaker.
Myself, O.P. Gupta, Director Central Water Acquisition. I have one question. What are the limitations of that model?
For our model?
Yeah.
Okay. First of all, in this model, we have developed mainly for research purpose. We have not tested for big field cases. Only 1 or 2 cases are there. Okay. So far it's working, but limited conditions are there. It's not like Mike 21, so many options are there. But dam break, partial dam breaching, that it can do without any problem.
And what are the boundary conditions you applied?
Boundary conditions means in this case, let's say, generally in the back side, we give the wall boundary condition, reservoir side.
Okay.
And
down
wherever there is breaching, that part as if it is not there in the DEM or the bathymetry. And we start from let's say if it is failing at 0 second, that means from that time we will consider the bathymetry without that portion. That portion is not there in the dam. Okay, and then we can
breach
start.
Breach parameters you have some
Breach?
Breach parameters. Dam
no, that thing is not, means you are telling the systematic breaching?
Yeah.
No, that thing I have not implemented. Like it is completely failure for a part of the dam or the entire dam.
Okay.
That thing I have implemented.
Thank you. Thank you.
Area you have to look at the modeling the structural failure processes for concrete dam as well as embankment dam, giving you duration.
Okay, in this model actually, we are considering the structures and all these things totally rigid.
So that is a point which we should, so it is not a panacea for especially embankment dams.
No,
you
no,
can't
not
assume
for
that
embankment
type of scenario.
I have to define the collapse area, like this is the failure portion, then it can do that inundation,
limitation.
Yeah.
Well, any other questions? Okay, then we move on to Parsan's presentation due to Rana. Medical checkup. I never go for medical checkup. I am afraid.
You must. Preventive health maintenance is better than what you have to do later. Anyway, yes.
But again, in your presentation, you have not given cost. I mean, how much is going to cost for the body checkup of the dam?
Right. See, this was actually a technical presentation, a technical paper, and I'll be covering the cost and commercial part of it tomorrow in a presentation. Yes. Okay. Right.
But the economic aspect is equally important.
Sure.
Because the owners of the dam, the states, they don't have money. And in order to be able to avail of the solution you have
I totally agree with you, sir. What I was trying to say was, sir, just like every dam is not the same, I'm sorry, it cannot be an inbuilt gradient. Just let me complete. Just kindly let me complete, sir. So, if you just want an idea, a typical investigation is start as low as 4 to 5 lakhs rupees and can go as high as 20 to 22 lakhs rupees for a range of dams, starting from small dams to the big dams. Like that's, I think that answers your question. Right.
Fair enough, fair enough. And so you are going to also let us know about the cost aspects. One more presentation, he says.
What is?
We wait for that.
Yeah, sure.
What is the time required for doing the geophysical approach for knowing the body of the dam?
Okay, see, it depends on, again, as my paper also deals with integrated approach, right? I never deal with one single method. So it depends on what is the kind of problem, what's the kind of dam, so what all methods we are going to use. But answering your question, just like I answered his question, it can range anywhere from 3 days to 10 to 15 days, maximum 15 days for even a large dam, with most of the methods being applied.
Yeah, is the results would be corroborated with the various methods?
Yes, that is the integrated approach. That is what all methods you are using. Ultimately, you have to put the results together and give an integrated output in terms of the internal condition of the dam. That is where yeah.
So you will give the output for each method?
We give output for each method. More importantly, we give the integrated output for the entire dam structure. Yes, we give it for the individual methods, which you might not be very interested in. Because again, going to medical example, if you go to a doctor with a pain, he gives you X-ray report, a MRI report, a ultrasound report, it might not be of much use to you. He would like to know what's wrong inside me, right? Similarly, we give the individual reports, but also the final this thing that what's wrong with the dam.
The cost you have indicated is for the integrated approach.
Sorry?
Cost you have indicated now.
Yes, it is for integrated approach, yes.
Thank you.
Thank you very much. We move on to the last speaker, Deepankar Chaudhary on DVC's Konar. Any questions, observations, suggestions? Well, yeah, please go ahead. Suresh Chan. Okay.
My friend spoke about the hydromechanical equipment and the problem with the Maithon or the Konar or the, DVC dams. As we were talking about the problem with the raising of the height or the capacity in order to increase the design flood or say to the PMF or that is one of the solution you gave, that the flood cushion can be increased and the FRL could be lowered. Now in this particular case, like Konar, I remember there was a request which was received by Central Water Commission way back to increase the FRL, not to decrease, but to increase the FRL. And I may remind all of you that the DVC dams, they were particularly designed for the flood control measures. That was the first priority, and the second priority was the utilization of the water. Now the situation has now come to such a level that now they have the state government and everybody has forgotten about the flood control business. They are more interested in utilization of the water. So in case the FRL is increased and there is a heavy flood comes, then what can be the state of affairs? I think, it is anybody's guess.
Sir, regarding this point, I want to mention a few points about the DVC reservoir system. That the Konar was built up mainly keeping in mind the conservation requirement, conservation zone, and the flood zone was kept lesser than the conservation zone. Main purpose of this reservoir was to feed the water to the Bokado thermal plant at downstream of the Konar, as well as to the nearby localities, industrial and industrial purpose. Anyway, but in case of the Tilaiya Dam, the flood cushion is more in comparison to the conservation zone. So there is a variation of the proportions of the reservoir zones. In case of the similarly Maithon, the flood cushion is lesser in comparison to the conservation. On the other hand, in Panchet, it is much, much more than the conservation zone. So this is the one point to be kept in our mind while taking the decision over these issues. And the second point is the increasing of the FRL. That is a debatable issue, and for that a lot of studies required, specifically the flood frequency analysis and the routing. Especially if I raise the reservoir levels, how it will accommodate, or I will have to change my operating policies, pre-evacuation, or like this sort of things we will have to think.
That is
even in
the point is well taken.
Yes, even in respect of the siltation aspects, I am telling you, very peculiar siltation behavior has been observed in this dam.
I think we are running out of time. The point is well taken. We would try to get focused on dam safety aspects and the reservoir regulation and other things. We, for a moment, keep it aside. That should not, try to cloud our minds while we think of the dam safety. I think we have everything covered. Some comments from the co-chair.
Thank you.
Mr. Suresh Chandra mentioned that state governments don't have even few lakhs to get that geophysical studies done. If that situation be, because now that situation has to change. If the dams have to be safe and populations have to be protected, the situation has to change. Dam break analysis, we may do anything, but God forbid, if the dam breaks, the volume of water will be so much, and the time to relocate the people will be so small, and thousands of people have to be moved out. That will not be possible. So, in that dam break analysis, they have set the stage 1. We have to keep the dams in the stage 1 only, that may be inspect and keep them healthy and don't allow anything disastrous to happen. So I think we should recommend here, leave this out as other things, but for dams, they should have dedicated funds for maintenance so that the health checkup is done regularly like we do for our body. Every 5 years with geophysical studies or any other thing, whatever has to be done in time so that the emergency situation doesn't arise, because we are not prepared. Under Indian conditions, we have such population and people are living in the flood plains, and there will be a real disaster, and we are already facing opposition for building new dams. If one dam fails, then it will be reason for all these NGOs and all that to sit on our head and not allow any further development to take place. So I think that should be strongly recommendation. Yes. Thank you.
Thank you. One of the strong recommendation as co-chair advocates would be to find somehow the money for the dam safety program in all its perspective. That is right from identification up to what you call restoring the dam to a healthy status. And more or less he also tried to tacitly bring out the need to make all the dams that we are trying to look at under this DSRP, dam safety or DRIP program, make it a fail-safe dam. That is, after doing all that is required and after taking all the actions that are necessary, it should be a sort of a fail-safe dam. So, notwithstanding other conditions like checking what happens in case of a arrest of rare event of dam failure. And for the new dams, it would always be done in a way that it is a fail-safe dam. This was the thing that we took a strong position when Terry was, questioned as to why it should be built, what happens if the dam breaks. The dam is under construction. We said a baby that is conceived is not conceived with the view to have some strong illness which would take it away. We would ensure proper pre-medical care, that the baby is born sound and would live sound. So something very similar, a fail-safe dam concept, at least for the dams to be built afresh, and also the dams getting revisited under the DRIP program. That is the message. Thank you very much, and we conclude.
I request the chairman to hand away the mementos.
Before we break, let us all agree to take a cut on our tea time by 10 minutes. We will try to assemble back here by 4:20. The tea time is 30 minutes, but then we will reduce it by 20 minutes. So we will assemble back here by 4:20.
Mr. Ramesh Nikum, if you could come on stage, please. I request the chairman to hand away the mementos. Mr. Antonio. Dr. Saumendranath. Dr. Sanjay Rana. And Mr. Deepankar Chowdhury. I request the chairman to also hand over the memento to our co-chairman, Mr. A.K. Ganju. Also, I request the co-chairman to hand over the memento to the chairman. Also, I request Mr. Ganju to hand over the memento to our reporter, Dr. Balaji.